Today's technical computing environment is dramatically different than it was just a few years ago. Technical organizations have a vast diversity of computing resources, which, if harnessed, could provide dramatic new levels of performance for the user. These resources include a variety of architectures, as well as specialized technologies that are now emerging for specific functions. The days of a single architecture being all things to all applications is passing by. Just as we've made tremendous progress in providing the user with access to a diversity of data, now the challenge is to provide equally transparent access to a diversity of computing. You probably already own several different architectures and want to take better advantage of them. You want to be well positioned to take advantage of new specialized technologies as they become available. Examples include database engines for fast access to information, super and mini supercomputers for high-speed numerical analysis, AI machines for expert systems, as well as existing systems from Digital and IBM. And let's not forget the computing power available throughout a network of workstations, each one with more power than mainframes of a few years ago. The challenge is to make all these systems play together as one interactive technical computing environment, allowing a single application to use this diversity of systems in a coherent way, even in parallel for highest performance. We're going to show you how Apollo's new network computing system helps you meet that challenge. We'll show you how the performance of this application can be increased 10 times by offloading the floating point intensive task to a mini supercomputer, and how you can use workstations in parallel to improve performance on this image processing application by over 20 times. By its very nature, network computing must be an open and portable system. Apollo is making the NCS specification public and providing source code to help users and vendors quickly adopt this exciting new technology. Just as workstation computing represented a major advancement beyond time sharing, we believe network computing is the next generation. That's why we are dedicated to leading the industry in this new area. Now, let's look at network computing in more detail.
The network computing system lets distributed applications share not just data, but computing power as well. With NCS, a single program executes on multiple machines. Parts of the program run locally, and other parts run on remote systems. A single program can even use multiple computers in parallel. Here's a fluid dynamics application that simulates the splashing motion of water. Attraction, repulsion, and gravity are modeled. Air viscosity is factored in. Even when we increase the number of particles, this DN3000 workstation provides impressive throughput. It's solving 56 simultaneous differential equations and displaying the results at 1 update per second. Good performance, but at the cost of some interactivity. Let's see how a specialized processor can return the interactive performance without major changes to the program. This application has 3 parts. One part of the program accepts interactive input. The second part solves the equations, and the third part displays the results. With virtually no modification of the application, we can offload just the compute-intensive portion to a mini supercomputer or mainframe. In this example, we are using the DSP-9000 mini supercomputer across an Ethernet connection. The result is much higher performance because the DSP-9000 has special vector processing hardware ideal for solving the matrix computations this application requires. So, with network computing, we regain interactive performance by using specialized hardware for a specific part of this application. The network computing approach lets both machines do what they do best. The mini supercomputer is an excellent vector processor, while the workstation provides the local computing power and graphics required for the rest of the application. This is a more efficient approach than running the whole application on the server and driving graphics terminals. It leaves the servers free to service a large community of users and lets the workstations handle all but the most compute-intensive tasks, thus ensuring that available resources are used with maximum efficiency. Another way to improve performance is to use CPUs in parallel, so a program running on one workstation can harness computing power throughout the network. Here is an image processing application that generates a 400-line image based on a mathematical formula called the Mandelbrot set. Computing the image is complex and takes almost 20 minutes on a single DN3000. But with network computing, we can compute individual scan lines on workstations throughout the network. The bars on the right show how many scan lines have been computed by each CPU. The result is a dramatic improvement in performance. What used to take almost 20 minutes, we can now do in just 53 seconds. Network computing is a natural outgrowth of Apollo's strategy to make our workstations the unifying technology that delivers productivity tools to the individual user. With over 1,200 applications, Apollo has the software solutions you need. And with our family of heterogeneous interconnect products, you get easy access to data and applications on a wide range of systems. For example, with our PC-AT coprocessor, you can run IBM PC applications such as Lotus 123 in a window. You can even move data from the PC screen into other windows. Our domain access product transparently incorporates the VAX VMS environment into domain, while our SNA product lets you use an IBM mainframe from your workstation. You can even have multiple sessions at one time, and of course, moving data is simple. Our IBM 5080 emulator lets you use an IBM mainframe to run applications such as CATIA and CADM. You can even insert IBM graphics into Interleaf for technical documentation. With the Apollo domain system, access to data on Apollo, DEC, and NFS systems is totally transparent. Just point at a file name and click the mouse to read the file. Whether the file is on a local disk, a remote network, or on another vendor's machine, the procedure is the same. Once we've made the workgroup more productive through transparent data sharing, the next logical step is to extend this openness to include compute sharing. While the domain file system and NFS address the data sharing component, NCS handles an important complementary area, compute sharing. The network computing system has two parts. One part of NCS makes it easy to develop network computing applications. The other part makes it easy to deliver and run them. The network computing kernel includes a remote procedure call runtime environment that handles computing requests, interfaces to the network, and converts data if needed. Another part of the kernel, called the location broker, lets applications find the resources they need at runtime. The kernel is designed for portability. It is written in C, and Apollo offers source code so computer vendors and end users can easily incorporate network computing capabilities. Let's look at how the parts of NCS actually work. We'll look at the steps we went through to convert the fluid dynamics application to use network computing. First, we ported the equation solver subroutines to the mini supercomputer. But we did not change the interface to these routines. They still expect to be called just like they were when they ran on the workstation. What we need is an interface routine on the client side that looks like the subroutine, and one on the server side that looks like the application. We define the interface using the Network Interface Definition Language, which is simply an enhanced C or Pascal style declaration. From the single interface definition, the compiler generates source code for the stubs on the client and server sides. The job of actually sending messages between the two parts of the application is done by a part of the kernel called the RPC runtime. The runtime is network and protocol independent and interfaces at the ISO layer 3 or network layer. This means that the network computing system works equally well on Ethernet, Token Ring, or other types of networks and protocols. The programmer doesn't need to know anything about the network being used. No application software has to be changed. If data formats between machines are different, the RPC runtime on the receiving side automatically converts the data. But if the two machines use the same format, the system detects this and no conversion is necessary. There are some important innovations here. The compiler that generates stubs automatically and the RPC runtime that's network independent make it easy to build network computing applications. There is a third innovation called the location broker. The location broker lets network computing applications find resources at runtime. When server processes are started, they register with the location broker. For example, the supercomputer might register its ability to handle vector algebra, matrix inversion, and image processing. The AI machine might register its ability to do design rule checking, while the VAX might register its ability to perform database searches. In addition, workstations can register their capabilities, so available computing power can be used to full advantage. For maximum availability, the location broker is replicated, and the network computing kernel includes a data manager that ensures that all brokers throughout large networks have the same information. Choosing the server machine at runtime required another innovation: dynamic binding. NCS provides 3 binding options: explicit, when an application always uses the same server; implicit, where it sets the server binding as a variable; and automatic, where the server to be used might change each time the subroutine is accessed. Apollo is actively engaged in recasting our own software product offerings to take full advantage of distributed computing power. For example, DSEE, our computer-aided software engineering toolset. DSEE's new concurrent builder transparently distributes the build of a software system across a network. This harnessing of unused CPU cycles around the network results in throughput improvements of up to 1,400%. Let's summarize the innovations incorporated in NCS and the benefits that network computing can bring to you. NCS is a portable, open system. It works with a variety of networks and adjusts automatically to your specific environment. This means that NCS protects your existing investment in computing systems and gives you more flexibility in your future computing investments. Network computing lets you take advantage of specialized processors and new technologies as they emerge. And it gives you higher performance for the ultimate benefit: higher productivity. For these reasons, we think you will agree that network computing is the next generation in technical computing.
Now that you've had a look at the concepts behind network computing and a look at the applications and the benefits of this new technology, we invite you to take the next steps. We have a complete technical information kit, including specifications, technical overviews, and application examples. We'd be glad to work with you on your network computing needs.